I had a night class up in Washington that I was teaching, and it was Monday, Wednesday, and it was a fall night class, Monday, Wednesday evening, and there were teachers that actually gave tests Wednesday evening before Thanksgiving, and I just couldn't believe it. I just yes, I agree. Disgusting. No regard for the lives of their students, you know. Anyway, okay, so let's go ahead and start here. Again, this is two practice tests, two space practice tests. If you want to pull that up. Okay, name the following. Okay, so this is just a plain old acid, an organic acid, and it's got 1, 2, 3, 4, 5, 6 carbons. So that's a hexanoic acid. And the other way you can see it drawn is like that. Okay, this is a acid salt based upon benzoic acid with a branch here. So this would be the main molecule, and then this would be the branch off that side chain. So this is going to be 1, 2, 3, 4. 4 propyl. Benzoate, because it's based on benzoic acid, and this would be potassium for propyl benzoate. Okay. This is a ether. So this would be the backbone on the acid part. And this would be the alcohol part, which would be a 3-carbon alcohol with a phenyl branch. So when you're naming ethers, you name the alcohol part first. So it's a 2-phenyl. Propyl. And this is a 1, 2, 3, 4, 5, 6 hexanate. So this would be alcohol. Okay. This is an ether. So that means this is going to be the acid part, alcohol part. So that's the isopropyl. And again, this is the acid here is based on benzoic acid. So this is going to be isopropyl. And it's going to be a 2-methyl benzoate. Excuse me. Okay, 3-bromo, 3-methyl hexanoic acid. Okay, so we have 6 That'd be 6 carbons. 1, 2, 3, 4, 5, 6. And 1, 2, 3. Bromo, 3 methyl. Now we draw structures that are ionic, and we have to do square brackets. And this is calcium. Square brackets, and butanoate, that'd be 4 carbons, 2 methyl butanate. Okay. So butanate is 4 carbons. And the calcium, because it's a alkali earth metal group, they all form +2 ions. So that would be what it looked like on 2 methyl, the methyl group there. Make sure you enclose the ionic compound in square brackets. So this is 8 carbons. One, 2, isopropyl. Xenon, 2-hexanone, the ketone, 3 methyl, 3 isopropyl. Okay, so we have a penta al. It's an aldehyde. And 1, 2, 3, phenol. Okay, so we have methyl octanate. That means that is an ester. This would be acid. This would be alcohol. So we have 8 carbons. It says, where can we find the other practice test recording? Did I not post Wednesday's recording? I can check that in a minute here. Yeah, we can do it real quick here. And 9, was that? It's 10/9 Monday, probably. I need to check and post last Wednesday's video. So it looks like I didn't do that. Yes, this looks like it's ready to go. I just haven't uploaded it. Yeah, I'll post all that. Let me make myself a note. Yeah. Okay. So sorry about that. Okay. So I might name myself a big note. In fact, as soon as we're done with this, I'll for sure I'll post last Wednesdays and try to get depending on my bandwidth today, how much will get posted. I've got a horrendously large download bandwidth, 450 um, um, megabits, and my upload is only 8, which is really strange. Anyway, okay, so this would be um, this would be alcohol, this would be the acid, 8 carbon, 1 carbon. Name a common biological energy molecule that is a phosphoric acid ester. Actually, there are 2 common ones. ATP and ADP. You see those a lot. So whenever ADP goes to excuse me, an ATP goes to ADP, you lose a phosphoric unit and you gain lots of energy. And the key here was energy molecule. If I just said a biological molecule, you can mention the ATP-ADP pathway. We also mention DNA, RNA. Oh, what else? Those are probably the most common ones. That DNA and RNA have a carbohydrate backbone using ribose sugar, and then those are tied together with a phosphoric acid ester. Okay, label the following molecules with all the intermolecular forces that may be appropriate for each. Okay, we didn't go into as much detail on intermolecular forces that I did in my past classes, but basically we've got hydrogen bonding, big time, hydrogen bonding, big time, So that would be number one, number two, number three would be, that's an aldehyde. So that would have, just a dipole, and this would have only dispersion forces. Everything would have dispersion forces. Now, for our class, I would not ask that question. I would ask it something like, put in ascending order boiling points or surface tension. So the higher the boiling point, you'd have to have higher intermolecular forces. So the hydrogen bonding is the most, actually ionic is the most, then comes hydrogen bonding. Hydrogen bonding is most with the acids, then hydrogen bonding with alcohols. Then we only have a very, very minor hydrogen bonding or just permanent dipoles with the aldehyde. And then this would just have something called dispersion force. And I mentioned that very briefly number of lectures ago. But the main thing I want you to focus on are these guys. Remember that graph that they had? Well, we had alkanes, aldehydes, alcohols, and then acids. As far as boiling point goes. So this question would be more in line with what would be on our test. Okay, so this, from now to the end of the semester, you can get more and more of these type of questions, okay? So we have a molecule, pretty complex, and what would the precursors be of this molecule for this one here? So this, we'll call this 1 and 2. Okay, 1 is a ketone, 2 is an acid. So remembering your chart, how do you get ketones? Well, you have to oxidize a secondary alcohol. You get an acid, you oxidize a primary alcohol. So what we're going to do now is we're going to add, we're still going to have the basic that's just going to tag along. So we have to redraw it each time, but it's not going to perform in any of these reactions, shaded reactions. It's just going to be tagged along. Okay, so let's do the first one here. So let's just draw the yellow structure first. There's that, that, and this goes like. This has to be a secondary alcohol. Let's see, don't have chlorine. Okay, so this secondary alcohol that secondary alcohol gets shaded, producing this ketone. Okay, and when I forgot to add the acid down here also here. Okay, so for number 2, this part over here, we have to redraw the yellow part again. And this time I'm going to start with the ketone version. We need to have down here a primary alcohol. So this would be oxidized first to the aldehyde. And you'll keep on going to the acid. Okay. So the part that I want you to focus on are the gray shaded areas, and the other is just baggage that you drag along, structuralize. So don't get intimidated by these massive structures. Just blow them off. Just say, what are we focusing on? What functional groups are we focusing on? And then using the reactions we studied in class, create those. In fact, since everything is being oxidized, you can actually combine both of these together. And anything that can be oxidized will be oxidized, which would be the secondary alcohol here, primary alcohol here. So if we had would take 3 oxidation reactions. This one here, we go to the ketone, so you can answer it this way or this way. Either one would be fine. We need some more time to draw this out. Excuse me. Yes, the 8 determines the ester. Okay, but sometimes 8 is used for forming an ionic compound, like that one ionic compound we drew up earlier, the calcium one, that also has an 8 as well. So there's both of those. Remember the calcium was an octanate or whatever. As soon as you bring in the ionic, this nomenclature comes into play too. So it's not an ester, it's an ion. Okay, that makes sense? Okay, so let's go on. Okay, which compound would be most, excuse me, God. Which compound will be most soluble in pentane and why? In your discussion, list any intermolecular forces interactions between the solute and solvent. Okay, so first of all, is a very, very nonpolar solvent. So like dissolves like. So which is most like pentane, hexane, or hexanol? Well, this is fairly polar. This is nonpolar. So hexane would dissolve more easily in the pentane than the hexanol. And the intermolecular forces involved is the only thing this has is dispersion forces. This has dispersion forces. This has dispersion forces plus hydrogen bonding, which makes it polar. Okay, so that's really important to remember. And you should remember this throughout your scientific career. Doesn't matter what class you're in, biology, biochemistry, or OChem, whatever, like dissolves like. So if it's polar, the solute is polar, polar solutes like polar solvents, non-polar solutes like non-polar solvents. And then to bridge the gap, you'd have an emulsifier like soap. Okay, we have a pH 9, that means it's alkaline. So the problem with this, it involves unit 3 because it's an amine. So I would not have this question on your test, but basically an acid like acetic acid, and we have a pH of 9. That means that this guy would grab that warm water plus the salt. And let's say we had a pH of let's say 2. You get no reaction. And where I was going with this, the amines act as a base and they do the exact opposite of what an acid does. So in a acidic environment, the amines are protonated by the hydrogen ions and become ionic. So this is ionic because it's a salt. Okay, so this is an acid chloride. And then we have an alcohol. So remember, there are 3 ways to make an ester. Acid plus alcohol, acid anhydride plus alcohol, and 3 acid chloride plus alcohol. That's hard to read. It's supposed to say yield. So the increasing yield. So acid chloride gives the most yield, acid plus alcohol gives the least yield. Okay, so we have an acid chloride alcohol. So we're going to end up with that H and that chloride form HCl plus. So this is ethanol. This is a 4-carbon acid chloride. Butyl acid chloride. And end up with a ester. It's going to be methyl. We're going to have a 4-carbon. Now I'm going to have line drawings on your test, not this carbon stuff. And again, this is a holdout because the text we were using up there didn't use line drawings, only used the carbon backbones with actual C's, which is kind of old world, I guess. All right. Okay, so we have an ester, and we have an alkaline environment. So this is going to be saponified. Okay, so this is the acid part, alcohol part. And because it's a saponified environment or an alkaline environment, we're going to end up with the acid salt. So this is a 1, 2, 3, 4. So it's a 4-carbon acid. So we're going to end up with this is going to be potassium. And then we're going to get the alcohol, which is a 2-carbon alcohol. So if we're going to name these, this would be potassium glutamate, and we have to go like this. For brackets. And of course, this would be ethanol. Okay, this is amines. This is unit 3. Okay. Okay, so what are we making? We're making an ester. Ester requires an acid something, an alcohol. Get an alcohol, we need an alkene. Get an acid, we need a aldehyde. Primary alcohol and alkene. And this is just looking on your chart. Okay, gosh, we have alkene, 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 alkene. So we're going to do this in 2 main steps. And then the third step, or the last step, will be combining the acid and alcohol into the ester. Okay, so let's take the first. Okay, so strand number 1, we need to get from the alkene to the acid. Okay, so we're starting with with 3 carbon. Two and 3 carbon alkene. I'm going to change this to make it a little different. Rather than 3 carbon, we're going to do a 2 carbon. Okay, so let's start with we're going to add some water, and then that's going to produce ethanol. I'm going to take that primary alcohol, we're going to oxidize it. That'll make that an aldehyde. I'm going to oxidize it again. And that'll make that okay. So that's our first line here. Let's go to the second line. So this one we need to end up with an alcohol. So we do the same reaction here. Let's make this a blue stone. Okay, so now we have an alcohol and an acid. So now we're going to combine those two to produce our ester. We're going to take our alcohol that we made, plus our alcohol, and that'll give us our ester. Well, everyone's gonna have trouble on this one. I agree. It would be in chapter, where is my book? Let me run and grab the textbook. This is gonna be in chapter 17. Chapter 17 is carboxylic acid and the derivatives, and the derivatives are esters. One of the derivatives is esters. Okay. But the problems in, let me check real fast, in chapter 17 though, are not multi-step. They are now skip the questions when they're talking about amides, which involves amines. We're going to do that in unit 3. Yeah, they really don't have any multi-step problems. So this would be hard to study from your book, but all we're doing here is we're just putting everything we've learned so far together. And this is why I'm saying that every test in OChem is cumulative. Because here we had to go back to our alcohols, and we had to go back to, into taking alcohol and oxidizing it, doing different things into aldehydes and ketones, and then oxidizing them. So it's just a multitude of steps. So this is why you're not having a final, because every test you take is a final. Cumulative. Okay. All right. So look at chapter 17. There's some really good problems in there, and I probably will be pulling from your book the take-home problems, because this is I really like this book, and it's got some really good problems that are thought-provoking in them, and obviously not the ones with the answers in the back. However, whenever you find a problem, there's a companion problem similar to it that does have the answer. So if you work the one with the answer, you'll probably have success working the one without the answer. That makes sense. Okay, so this obviously has the most points because it's the most involved, the most parts to it. Are there any questions about this test?
I have a quick question, and I feel like I've asked this before, but I don't remember what you said. For Unit 1, we had a printout of all reactions that you gave us out in the beginning of the test. I was wondering if for this approaching exam, you will also have something similar, just to show us what happens if there is saponification or esterification and all of the other reactions, if you have a printout with like arrows pointing to which reactions will occur.
I mean, other than that chart I gave you?
Like the one you gave us in Unit 1?
Yeah.
Yeah, something similar like that for this unit, because there is more reactions and different reactions happening with everything we've learned.
Yes, I do have a combined one. Let me post that too. Now, at the back of each chapter in your book, they also summarize reactions, not quite like the way I did it, For example, on page 543. Mine is really different than the way to do it, but between the two of them, you should have both and look at both of them. But there's some really good questions in this book. For example, if you look at on page 542, there's a problem on there's a compound called acetyl coenzyme A, and they gave the structure of it. And when you look at the structure, it's stuff that we've already studied. And so you can, from there we can ask questions about it. How would you synthesize this from precursors or whatever? But anyway, let me post the rest of the charts that should go into a little more detail, and then see if that answers your question.
Okay, thank you.
And then I'm trying to think, before I leave for lab, I'm going to have a little bit more time. Well, not a little more time, but to post some of the stuff. And then you have lab today, right?
Yeah.
Okay. So look at the stuff I posted in a little while and see if that answers your question.
Okay, sounds good.
Good. No open notes. Okay, and then I have this is the key. I did this key a long time ago, so I should probably look at it and make sure it should have all the same answers as now what's different are I'm using C's here instead of line drawings. And also using the instead of 2 carbon, this is a 3 carbon. And I modified this to be 2 carbons. So okay, any more questions? Okay. Now, interestingly, our lab today is we are taking now salicylic acid and acid aldehyde, but it's got there's an ester, and then that's going to act on the acid or the alcohol part of the salicylic acid. So salicylic acid is both an alcohol plus an acid. Their aspirin is going to look like So aspirin is an acid and an ester combined. So if you have old aspirin, it kicks that off and reforms the alcohol. So old aspirin oops, not HCl. So old aspirin has a vinegar smell because the ester breaks up into the acid, part of the ester, and the alcohol. So when we get today you're going to be getting some old aspirin to test and smell it, see what it smells like. You should have a vinegary smell to it. And that's where the aspirin is coming apart. Now, salicylic acid also has some, it's considered an NSAID as well. It just isn't as effective as aspirin. NSAID is non-steroid anti-inflammatory drug. And that would be your ibuprofen, Tylenol, aspirin, salicylic acid, almost anything except the steroids. And they all act on arachidonic acid to form a prostaglandin. And there are two kinds of prostaglandins. One's good, one's bad. Anyway, that's what we're doing today. So it's a really cool lab. I've done this lab a whole bunch of times, and almost each school likes to do it differently. So Sac City is doing it differently than I normally do it, but basically you end up with aspirin. And then the week after next, we're going to take your aspirin that you made and we're going to go into the instrument room and actually look at its infrared spectrometry. And we're going to talk about the different tests. We're going to have this is a phenol. So there's a phenol test using an iron solution that we're going to test for. And we should have all the salicylic acid reacted when we make our aspirin. If there's any left over, we'll end up with a positive phenol test. Also, the infrared analysis will show us whether we have a mixture of aspirin and salicylic acid, or just salicylic acid, or just aspirin. And we'll learn how to read that. We'll also do a melting point on it, because salicylic acid melting point is different from aspirin. We'll also do a flame test as well. That'll be a follow-on lab to this one. It should be. This is a really cool lab. You guys should like this. Okay. All right. Any more questions?
Professor?
Yeah.
It's next Monday, right? The test in lab.
It's next Monday or Wednesday, depending on what lab section you're at.
Okay, thank you.
You're welcome. Now, in your lab write-up, do they mention whether this was in pairs or groups of 3 or 4? Did it mention that? I don't remember what it said. I just have to look at that. At least in groups of two. The problem is you're not be doing it in the hood, the filtration. So we'll probably end up, depends on how the lab is set up in the hood, whether we have one filtering per hood or two filterings per hood. And the middle hood, you only have one group in there anyway. So really there's a possibility of either 3 or 5 workstations in the hood. And I'll use that number to determine how big the groups are. Okay, so if there are any more questions, I'm going to end this now. And we will see you in a little while for the Monday, folks.